So our last day of notes in this unit, we're just going to tie together everything we've learned and go back and review every single thing so that you can get the best score possible on this vector chapter test coming up. So the first thing to understand is that there are three standard unit vectors. There's I, which takes you 1 unit in the x direction. There's j, which takes you 1 unit in the y direction. And there's k, which takes you 1 unit in the z direction. Now you can use negative i's if you want to go left, you can use negative j's if you want to go down, and negative k's if you want to go away from yourself. Positive k's would be towards you, negative k's would be away from you, according to the right-hand rule. And so each one of these you move exactly 1 unit in a specific direction. When we want to create vectors that go more than 1 unit in a particular direction, you just put a coefficient in front of each one of these. Vector v is an example of a three-dimensional vector because it's traveling in 3 different directions. 3 units in the I direction, 4 units in the j direction, and -5 units in the k direction. Whereas vector u is actually only a 2-dimensional vector because it's only traveling in 2 directions. -7 in the I direction and +8 in the j direction. Make sure for both 2-dimensional and 3-dimensional vectors that you know how to find the magnitude. Magnitude represents the total length of a vector, and it is found by using Pythagorean theorem. Now there is both a 2-dimensional and a 3-dimensional Pythagorean theorem, so you're going to have to know both of them for this vector test coming up. So let's practice. If somebody asked you to take the magnitude of vector v, you would take the square root of all 3 of its coefficients squared. So 3 squared plus 4 squared plus, and put this in parentheses, -5 squared. You're not just squaring the 5, you want to square the negative along with it as well. So 3 squared is 9, 4 squared is 16, 5 squared is 25. When you add all of those up, you're going to get the square root of 50, which of course is going to be simplified into 5 radical 2. The magnitude of vector u, that's this one right here, since it's only 2-dimensional, is going to use the 2-dimensional Pythagorean theorem. We're going to be squaring -7. Again, put the negative numbers in parentheses so that you remember you're squaring the negative as well. And also squaring 8. So this is 49, this is 64. When you add that up, you're going to get the square root of 113. If you could simplify this, you should, but square root of 113 doesn't simplify. So remember, 2-dimensional vectors don't have the third part. They only have the 2 pieces, and the 3-dimensional vectors do take the magnitude using all 3 parts, squaring, 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 adding together, take the square root. The next thing that we took a look at in this unit was operation vectors. So we should be able to add and subtract. Remember, with adding and subtracting, you're only adding or subtracting like components. So i's go with i's, j's go with j's, k's go with k's. If somebody asked us to add vector v and u, even though one's 3D and one's 2D, you could still do it. For vector v, we got 3 i's, and for vector u, we have -7 i's, so that would be -4 i's. And vector v has 4 j's, and u has 8 j's, so that'd be a total of 12 j's. And last but not least, vector v has -5 k's, and u doesn't have any k's, so -5 k's plus no k's makes -5 k. So this would be the sum of those 2 vectors. With subtraction, you've got to be very careful. Number 1, order matters, so they've decided to put u first. And then you also have to remember to distribute your negative to all the terms, all the components in the second vector. So we're starting with -7i, and we're subtracting 3 i's, which would make -10i. We're starting with 8 j's, and we're subtracting 4 j's, so that's going to make 4 j's. And we're starting with no k's, and we're subtracting a -5 k, so that would actually make +5 k. And then last but not least, one of the easy kinds of multiplications to do is what's called scalar multiplication. That's when you're multiplying a vector by a constant. Just make sure you're distributing the constant to each and every one of the components of your vector. So if I have 3 times vector v, I'm going to triple the i's, making, in this case, a total of 9 i's. I'm going to triple the j's. There used to be 4, but now there's going to be 12 of them. And I'm going to triple the k's as well. There used to be -5. Now if I triple that, there's going to be -15 k's. So another kind of multiplication that we learned how to do with vectors in this chapter was something called dot product. And dot product is going to show us literally a dot in between the two vectors. So what you do for dot product is you multiply the coefficients from like components together. So the i's coefficients together, the j's coefficients together, the k's coefficients together. You don't put the i's, j's, and k's on the back end of them, just the numbers. And then you add those 3 products up. This makes a scalar answer. So you should never get a vector from doing a dot product. It should always just be a scalar. So let's practice this. If we have vector A, which is 3i minus 2j plus 4k, and vector B, which is 6i plus 15j minus 5k, and somebody asks you to do the dot product, see the symbol dot in between, we're going to take the numbers from in front of the i's, 3 times 6, which is just 18, and then we're going to take the numbers from in front of the j's, which is -2 times 15, which is going to be -30. And then the coefficients from in front of the k's, which is 4 times -5, which is going to be -20. Putting this all together, you're going to get an answer here of -32. The answer should just be a number. There should not be any i's, j's, or k's whenever you're doing a dot product. Now, a more complicated kind of multiplication that we do with vectors is something called cross product. And the symbol for that is a times symbol, or like an X. And this makes a completely new vector. And what's special about this new vector you're making is that it's perpendicular to the 2 vectors that you started with. So if somebody asked us to take the cross product of A times B, this is the symbol we would see in between. Here's your vectors up here, 3i minus 2j plus 4k, and 6i plus 15j minus 5k. So the first thing you do is you make a 3 by 3 matrix. And into that top row, you put the standard unit vectors, I, j, k. Into the second row, you put the coefficients from whichever vector came first, in this case, A, so it's going to be 3, -2, 4 across the middle row. And the third and bottom row is going to be completed with the coefficients from whichever vector comes second. So in this case, vector B's coefficients are 6, 15, and -5. They're going to go across the bottom. Once you've completed your 3 by 3 matrix for the cross product, you want to find the determinant for this matrix, which requires that you copy the first 2 columns next to your matrix so that you can finish all your diagonals. Here we're going to have 10i, and that's going to be 24j. And that's going to be 45k. Then going the wrong way, this was going to be -12k, but it's going the wrong way, so minus minus is the same as adding 12k. And this, it was going to be 60i, but it's going the wrong way, so we're subtracting 60i. And the last one was going to be -15j, but it's going the wrong way, so we're going to add 15j. All right, now what ends up happening here is you get 2 of every kind of component. You're going to get 2 i's, 2 j's, 2 k's, so you should collect like terms. Putting your i's together, it's going to give you -50i. Putting your j's together should give me 39j. And last but not least, putting the k's together, I think I've got 57k. Remember, cross product is not commutative. So if somebody gave me those same 2 vectors and I put them in a reverse order, I'm going to get exactly the opposite answer. So same numbers, but every single sign will be the opposite of what you had. That's called anti-commutative. Dot product is commutative. cross product is anti-commutative. So the next kind of multiplication that we're going to take a look at is what's called the triple scalar product. You're going to need 3 vectors for this. So we've got vectors A, B, C over here. And what you want to do, what you want to know about this is you need 3 vectors, and it makes a scalar answer. So the answer to this should just be a number. No i's, j's, k's, no direction, just a number. You're going to make a 3 by 3 matrix as follows. You're going to make the top row equal to the coefficients from your first vector, second row equal to the coefficients from your second vector, and the third row equal to the coefficients from your third vector. So if I'm putting A in front of the dot product and then the cross product of B and C inside of parentheses, that means A is my first vector and its coefficients 3, negative 2, 4 are going to go across the top row. B being the middle vector in this, its coefficients 6, 15, and negative 5 are going to go across the middle. And C, with it being last, is going to be the bottom row of the coefficients, negative 2, 7, negative 1. And so again, to find the triple scalar product, you're going to take the determinant of this 3 by 3 matrix. So here we have negative 45, and then that's going to be negative 20, and that's going to be 4 times 42, and so 4 times 42 is positive 168. Gotta get my calculator. So that ends the 3 diagonals that go this way, and now we've got 3 diagonals coming back the opposite way. Negative 2 times 15 times 4 is going to be minus 120, which is like adding 120. And then this is 3 times negative 5 times 7 would be negative 15 times 7, which is negative 105, but it's going the wrong way, so minus is like adding the 105. And last but not least, this is 12, but it's going the wrong way, so we're subtracting. If you put all these answers together, I don't expect you to do this in your head, if you put all these answers together, you end up getting an answer of 316. Now again, remember, dot product is commutative, but cross product is anti-commutative. So if you put these vectors together in a different combination of order, you could either get positive 316 or you could get negative 316. There's actually 6 different combinations you could put this together with. So 3 of them give you positive 316, 3 of them give you negative 16. The last thing to review, and I saved it for last because this is probably the hardest thing in this chapter, is how to convert back and forth between polar and rectangular vectors. So this is just going to be for 2D. We're not going to do converting between polar and rectangular in 3D. This would actually be called spherical coordinates. If you go on in math, you'll learn that. So let's say we have a vector. One way you can express it in rectangular form is the way that we've been doing. A certain amount of units in the I direction, a certain amount of units in the J direction. This makes your math super easy. The problem is, in physics, they oftentimes give you your vectors as polar coordinates, which is a total magnitude, or length, and then comma, and a directional angle. This angle theta is always measured in standard position, so it starts from the positive direction of the x-axis and rotates around counterclockwise if it's a positive angle. So if you're trying to go from rectangular into polar, this is the harder one, by the way. To get your total length, you'd have to do the Pythagorean theorem to find the magnitude of a squared plus b squared underneath the radical. And this is the tricky part right here. The directional angle would be the inverse tangent of b divided by a. Now, that's your y component divided by your x component. But remember, the limitations on inverse tangent make it so that only works from negative 90 to positive 90 degrees. So you're going to have to check what quadrant the calculator says you're in against what quadrant your vector actually should be in. If they match, then your calculator is giving you the right answer. If they don't match, your calculator is giving you a reference angle, and therefore that reference angle would have to be added with 180 because you're trying to go to the left, who's referencing from 180. Now, if you're coming back in the other direction from polar back to rectangular, it's a lot easier. There's no worries about trying to do inverse trig. Your A component, which is in the x direction, is going to be your magnitude times the cosine of the angle, and your B component, which is in the y direction, is your magnitude times the sine of the angle. So let's practice on a few examples of this, and then you'll be ready for the practice. So I have two different examples here. In our first example, we're going to try converting a vector, which is currently in rectangular form, negative 3i minus 6j, into polar form. So there's two parts to this. First, you have to come up with the overall length, which is just magnitude. So we'll be taking the square root of negative 3 squared plus negative 6 squared. Now remember, lengths cannot be negative. So when these things get squared, they're going to be positive and then they're going to get added together. So this is 9 and this is 36, which initially gives you a length of the square root of 45. But if you get a radical that can be simplified, you should. And 9 is a perfect square that divides evenly into this, so that's going to give you 3 radical 5 as a simplified radical form. And then for the directional angle, you're going to be taking the inverse tangent of the y component, which is negative 6, divided by the x component, which is negative 3. So in other words, we're taking inverse tangent of 2. And the calculator is going to tell me that the directional angle should be 63.43 degrees. However, 63.43 degrees is clearly in quadrant 1, but if I go back here and look at the vector, it's going 3 units to the left and down 6 units. That's not in quadrant 1. This vector is supposed to be in quadrant 3. So what that means is the calculator has given me a reference angle, and that means I'm 63.43 degrees away from the x-axis in quadrant 3, which would be 243.43 degrees. And that's your directional angle. That is the angle that would take you into the third quadrant, 63.3 degrees, 63.43 degrees away from the x-axis. Now, going from polar back to rectangular is very, very easy compared to this. You don't have to worry about reference angles. You're literally just going to take your magnitude, which in this problem is 43, and multiply it with the cosine of the angle to help get your I component. So again, make sure that your calculator is set in degree mode. 43 times the cosine of 126 is going to be negative 25.27. And that's going to be the amount of the vector in the I direction, because your A component goes in the I direction. And then magnitude times the sine of your angle. So 43 times the sine of 126 degrees will give you the amount of your vector going in the y direction. So that would be 34.79 in the j direction. So make sure that you put the labels on here with the i's and the j's so that you know how much is going in the x direction, how much is going in the y direction. Okay, with that review, you are now ready to try the practice test. There's a practice test and there's also solutions for the practice test. Please give these a try before you actually try the test tomorrow.